this is a two-dimensional collision, and we're going to keep it quasi-simple. And just, these are traveling in the x and y axis independently. It makes it easier. All right. So we have object A is traveling to the right at 3 meters per second. It has a mass of 2 kilograms. Object B is traveling upwards. You can say like that's to the south and that's to the east or whatever. And then 2 cars, pretty small cars. This B is traveling at 8 meters per second and has a mass of 1 kilogram. They collide right here. Collision right there. Ah! And they combine, they go off together, stuck together with some speed after the collision at some angle. So I'm going to treat this as a perfectly inelastic collision. They collide and stick together after the collision. What is their momentum after the collision? What is their speed after the collision? How fast are they traveling immediately after the collision? And what angle do they travel at? Well, this is perfectly inelastic, as I said. And momentum is conserved in the x-axis. And momentum is conserved in the y-axis before and after the collision. So to solve this, we have to look in the x and the y-axis. X-axis. Before the collision in the x-axis. After the collision in the x-axis. Momentum is conserved. Well, what is the momentum in the x-axis? Well, the way that I designed the problem, it's all coming from object A, because object B is solely in the y-axis. So this is going to be PAX naught plus PB x naught, which there is none, equals the x component of the momentum after the collision. And what is this? This is the mass of A times its initial velocity. So what's px? It's going to be 2 times 3 is 6. 2 times 3 is 6. So yeah, px is equal to 6 kilogram meters per second. That's the x component of this. So the first thing I'm going to actually find is p afterwards. And here is its x component. Px equals 6. And then let's do the y-axis in green, just for the heck of it. So what I'm looking for now is that. Y-axis before the collision, after the collision. Before the collision, you've got the momentum of A in the y-axis, which is 0 because it's all on the x-axis, plus the momentum of B in the y-axis, and that will equal total momentum afterwards in the y-axis. So all of the momentum of object B beforehand becomes the y component of the momentum of the system after the collision. Before, after. So by the same token, all of the momentum in A before the collision becomes the component of the momentum after, in the x-axis after the collision. So the momentum of this is 6, 2 times 3 is 6, so that's why this is 6 afterwards in the x-axis. This will be 1 times 8 beforehand for B, and that becomes the y component of the momentum afterwards. So the mass of B times its velocity. That's 1 times 8. So Py equals 8 kilogram meters per second. Now I'm going to erase this because it's just too messy. We already know that that's 6 and that's 8. All right? So the x component is 6. The y component is 8 kilogram meters per second. Pythagorean theorem will give you the actual momentum of the combined unit. The square root of 6 squared plus 8 squared is 10. All right, 6 squared plus 8 squared is 100. Square root of that is 10 kilogram meters per second. The angle, well, the arctangent of 8 over 6, all right, tangent of this angle is opposite over adjacent. 8 over 6 is 53 degrees. So this is 53 degrees. So the momentum after the collision of the system is 10 kilogram meters per second, and the angle that it goes off at is 53 meters per second. The last thing we need to do is figure out the actual speed of this thing, and that's fairly easy because we know that the momentum of the system equals the mass of the system times its speed. That's 10. The mass of the system is 1 plus 2 is 3 kilograms. Again, this is of the system. 3 V. And so, is that right? Sure looks like it. So V is going to be what? 3 1/3, 3.3 meters per second at 53 degrees above the horizontal. So there's your angle, there's your momentum. The speed and the momentum, the velocity and the momentum are at the same angle. Done.